discussed that to find out whether the model is overfitting or underfitting. Because what will happen is in both cases, overfitting or underfitting, we will get the bad error, as in the error rate will be very high on test data. Now, when the error is high on test data, what you do is you go back and check whether the data it's overfitting or underfitting. So instead of that, what we do is we use cross-validation, right? As outlined in the end-to-end project. So that end-to-end project basically covers this part, that we do the cross-validation, we get a fair amount of idea. In case the model performs well on training data, it generalizes poorly on according to the cross-validation, the model is overfitting. Basically, when the model is too complex, it will overfit. A model is too simple, it will underfit. I hope everybody is clear about it. Okay, actually title of this notebook should be training models, not linear models, because we just learned about nonlinear also. All right, please note that the gradient descent and other technique remain as such. Gradient descent technique remains as such when we go for polynomial, but the normal equation doesn't remain like this in case of polynomial. Okay. Because what happens is that in case polynomial, we can't really solve it that easily. Therefore, the normal equation cannot be used so easily to get the results. Also, when the number of features keep on growing, the normal equation becomes more and more difficult to get the outcome. All right. So most of these ideas are pretty simple, and we in normal life, we actually get these ideas really quickly. Just that the word and the verbiage, as in the text, is basically the new terms are there. That's why we find it uncomfortable. Though in normal life, we get all of this really easily. There was one more question from Bo, that what does I plus mini batch size do? Okay, so line number 22 and 23, right? So what's happening there is we are taking first 20 records, then we are going to so what we are doing is, I'll just show you. Can you see my screen? And let me try changing. Ouch. I increase the font. It's going to take some time to re-render it because the notebook is a little too big, and the browser's memory is the constraint here. Probably we should just break these notebooks into parts. Because this is causing a mental block. Now where was that? Oh, here, right? We were stochastic gradient descent. Then we are somewhere here, mini batch. Question is from Bo is that what does I plus mini batch size? So what we are saying, start at 0, go up to 0 plus 20, correct? Let's say I was 0 in the first time, right? So 0 to 20 will go in xi, right? And similarly for y, 0 to 20. Now in the next time I will be 21, correct? I will be 20 or 21, okay? And then it'll be 20 to 40 and 20 to 40, like that. Yeah. So basically we will select, here we are saying start at 0, go up to 20. Then in the next iteration, it'll pick the next 20 records, starting with 21 up to 40 and so on. So if you look at this, all right, so we are saying that for I in range 0, let's say this is say 100, right? And let's say mini batch size is 20, okay? And we say print and from %s to percentage as, right? Let me just say I, and I plus, what was the mini batch size? Say 20, correct? Right now, this is the mini batch size, okay? I'll just define it here so that it's a little more clear. Let's say 20. This is what's happening. So you can see, saying pick from 0 to 20, then 20 to 40, and so on. Great. Wonderful question. So yeah, this we have defined here. All right. So and we are putting an epoch here. Let's say for epoch. So what's happening is the question from Deepak was that why do we have, let's say number of iterations. Okay, be with me for a moment. I think what we all need to do is make a very freehand approach. Okay, make a very freehand approach when we are dealing with this code. Try writing your own code, insert new cells, and try experimenting and tweaking with things. Make yourself very comfortable, right? And the other way is just okay. So like that. Now you see that here we are see the epoch now for epoch, and this we are increasing this. Okay, now we are unnecessarily printing it here. Okay, now I can see for 0th epoch the same thing happened, again same thing happened, and so on, right? That, so that's what is happening over and over, correct? So this is basically these many times that loop will run and thetas will be tweaked. Perfect. Okay, so try tweaking these values, try seeing that what's going on here. It's good that you are looking at the code and making yourself comfortable. Make yourself comfortable because this is like really simple code. It sounds like complicated gradient descent, but it's not. Only this part is basically a formula that we had discussed earlier, and it's okay to even assume that we know this. Okay, it's completely, you know, okay to just for now just memorize or just keep it a note which you can copy it, but rest of the code you should be clear about. Okay, all right. uh, and great, so that was one thing. So here we talked about earlier we talked about something called learning schedule. Have we talked about learning schedule, right? So instead of I think learning schedule will come. Okay, we've already talked about learning schedules. Okay, so learning schedule is basically here what we are doing is we are decreasing the instead of keeping the learning rate like eta as fixed, right? We are tweaking it. We are decreasing or increasing eta. Instead of having fixed value, we are letting this function decides, right? We're letting this function decide the eta based on this one. A question from Jay is, in calculating gradients, t is the part of formula or variable? T is the, while calculating the t is, which t we are talking about? This small t. Capital T. Oh, this is, thank you for asking that question. This is basically transpose. Okay, you can just, I'll just show you what it means. So if we have X, right, or let's say um, the transpose, remember the transpose which we did in case of NumPy, basically converting rows into this. So when we say xi dot t, it's going to take xi tilt it such that the columns become rows, or you can say twist it such that columns become rows and rows becomes columns. Okay, so xi.t basically calculates that transpose. It makes you feel that it's a variable, but right. Okay, and yeah, and this dot you see, this is basically a dot product. This dot this. Okay, which okay, all right. Let me just run everything till here. All right. So which code do you want me to paste? The one I wrote, actually I deleted that code. And all right, great, great. So let's say we have some value like xb suffered. You see, it looks like this, right? 0, 1, and so on. Now notice only these two values, okay? 0.56. You can just say dot t and take a look. Now this is now became kind of vertical, right? So this, so you can see this is the first column now, and this is the second column. So you can take a simple example that will make you clear. Perfect. Moving ahead. So perfect. So we talked about the basic ideas about the epochs and the batch gradient descent and the stochastic gradient descent, and we also talked about the learning curve. Now, one way is the way that we learned in Entrant project was that we use cross validation to see how is our model doing with respect to the data. So first we divide the test in test and train. That's obvious. So we keep the test aside. We only pick the train, and in the train, what we do is we do the train set. The training set, what we do is we do the cross validation, right? Cross validation basically makes it run the makes trains your one model on say 90% of data, and then tests on the remaining 10%, and this 10% is chosen iteratively through the through the 10% is chosen iteratively through the 10 sets. Now the learning curve is the another way of figuring out the overfitting and underfitting. This is an important part, so please pay attention. Why I say important part is because some of the candidates were appearing for there is a position called machine learning slash sorry, the data engineer slash machine learning position at Google. They were asked about mostly about learning curves. All right, and these ideas remain common between the deep learning and machine learning, and we will be covering mostly those ideas that remain common between machine learning and deep learning. Okay, now the learning curves are the plots of models performance on training versus the validation set, right, as a function of training set size. So we generate the plots. Basically, we train the model several times on the different size subset of the training set, and then observe the plots. All right, I think the plots, when we right, when we see the plot, then it'll make more sense. So we'll train the model on different subsets of data and then plot the RMSE and training set size. Now, where are we? We are somewhere here. Probably I'll just keep pressing Shift Enter, going down. Yes. Okay, it did plot something, right? Okay, it's plotting something. Okay. Let it finish. Okay. How much time is going to take? Oh, because the training is probably going on above. Okay. Okay. So where it is it stuck? You will see yeah. I think it's doing this iteration because there are just too many iterations. So I'll just interrupt the kernel. Okay. So I'll just skip this part. Okay. It's going to take a long time. Why is it taking so much time here? Ideally, it should not take so much time, right? Again, I'm interrupting the kernel. Also, I should change the number of iterations from 20,000 to less so that this iteration doesn't take forever. Any idea why is it taking time, or is it just because of kernel interrupt? Let's say kernel interrupt again. And I say here that 2 plus 2. Oh, there's something wrong with the kernel itself. So looks like kernel is still stuck somewhere. Okay, I'm restarting the kernel. Okay, and then I'm saying cell run all above, right? All of this is done. We've already done it. We are done through this. And yeah, we say run all above. Okay, so I've restarted the kernel. I'm hoping that it should run fine. Where are we right now? The execution is probably here. Yes. All right. So looks like it's done. All right. Perfect. Right. Right. So what we have done here is we have plotted. Okay. Um, so question from Robert is that's why I prefer coding with PyCharm so that I do the debugging. Actually, you can do the debugging here pretty well. Okay. Make yourself extremely comfortable with the notebook, and probably from next to tomorrow onwards, what we'll do is we'll add maybe a couple of more servers so that it's going to be a little better. Or what we can do is we can split these notebooks into multiple parts. Okay, like we could say training model and score, gradient descent, and then learning curve and so on, so that it becomes easier and manageable. All right, it's actually I find it quite comfortable with the notebook, and you will also find it very comfortable. Though PyCharm is definitely great, but for interactive computing, I find this far more easier, specifically for the machine learning parts. Now, but most of the work which people do with respect to, say, development of web server application, in that case, I think PyCharm does a far better job than this. Okay, now coming back to it, let's just walk through this code and make ourselves comfortable with the idea of a learning curve. So what we are trying to do is we are trying to achieve this. We are saying that as the training set size grows, how is the error? Okay, and we are doing that on both the training set and the validation set. Okay, so we took some training set, right? We took some training set size, right? And then trained the model on that and tested the model on that. Let's say if we took first few records, like 10 records. On 10 records, this is how it looks like. On 0 records, or on 1 record, let's say, on 1 record, the performance on the training set is this, and performance on the validation set is this. You can see when we are training on a very small data, the model is having a huge performance difference, right? The root mean square error is really high. As the training set is increasing, when we are training on the larger set, what's happening here is that the 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 validation, the error on the validation has become kind of fixed as we are increasing. When the data set has gone to, say, the validations, the training set has gone to, say, 70, the error has the error is not reducing with respect to the validation, but you can see that the error the error on the training set has also stabilized. Okay, so when you see this happening, it means both the curves are touching here. Both the curves, the training set, the curve that represents error on the training set, as well as the validation set. When both the curves are touching, meaning the error on both is similar. Okay, that means that here we can say that the model is basically having has achieved good point, meaning it can't, because as these two lines touch, that means that there is no overfitting, right? Probably it could be underfitting. Maybe if you want to improve the RMSE now, either we go for some other model, or we make this model more complex, maybe introduce some more degrees and some more polynomial degrees and so on, right? When you see this, when these two lines are touching, when these two lines just touch each other, that means you are good. Okay, because you have kind of is not overfitting. But if you see at any point of time, the error on the training set going to be really low, like here, right? The error on the training set is, say, 1.2 here, 1.3 here, and the error on the training set is, validation is really high. What does it mean? It means that it is sort of overfitting. It is sort of overfitting. So this way you can see that in the beginning, when the training set is smaller, it is overfitting, but as the training set keep increasing, the model has become it's not overfitting anymore. Okay, so that's what we have done here, and let's just walk through it. So we've created something called method called plot learning curve. Given a model, we give x and y. So first of all, what we are doing here is we are splitting it into training and test, right? Training and test. And after we have split it into training and test validation, what we do is we iterate over the training set size, right? And what we do is we are saying that fit the model up to m, data size, right? First, and m is going to vary from how many? It's going to iterate over 1 to the total number of instances. If the total number of rows are 1000, m is going to vary from 1 to 1000, correct? So first we will train the model on records up to 1, because m is going to be 1, 2, 3, and so on. So colon 1 means train this model on the data from beginning till 1, till 2, till 3, till 4, and so on, right? So it's kind of incrementing. So we are doing that, and then we are also doing the predictions. Okay, we are doing the prediction on the training set. Okay, so here this is the training set predictions and this is the validation set predictions. Okay, all right. Also, we are here predicting on only that part, whichever we have trained on. Okay, whatever we have trained on, we are predicting on that exactly. You see, we are doing model.fit and we are doing the model.predict on the same subset of the data. So this is called, we are trying to do the predictions on the same set on which we have trained. Similarly, we are doing the prediction here based on the validation set which we had kept separate in the beginning. Okay, we kept a certain part of the data separate in the beginning. We are doing the prediction on that, right? And then we are computing the mean square error of both of them, this and this, both training and validation, and then we are appending them to this error, training error and validation error. And once we are done with the creating this full arrays, these two arrays, we are plotting these two arrays here somewhere. We are saying, yeah, we are saying the square root of training error and square root of validation. We're plotting these two. So this gives us this one is in red color, this one is a blue color. We are saying that it should be plus, it should be, this is the format of the line. One would be like with having this kind of pluses in the line, and the other will be nothing, it will be straight line, like, right? So this is good for people like me who are colorblind with the lines and so on, right? And now going ahead, so what we have here is this, what we have once we are plotting it, we get. So what happened was we trained with, let's say, one record, and on the same record we did the prediction. It gave a great results, like perfect result, maybe close ones, and this one gave us a bad result on the validation set. All right. So I hope this is clear what we've done here. So essentially what we've done is we have plotted the performance of the model. We are training it first on first record, then on first two records, then on three records, then we training it on first five records, and we are testing it on the same records as well as on the certain validation set, right? So so you can see that when there is just one or two instances in the training set, the model is fitting them perfectly. That's why the curve starts at 0, and that's overfitting, right? Because so here, which is why the curve starts at 0, and but as new instances are added to the training set, it becomes impossible for model to fit the training data perfectly, but both because the data is noisy and because the data is not linear at all, right? And the error on the training set data keeps going up until it reaches the plateau. Okay, so meaning when you are studying more and more, your error on the same textbook which you studied should go higher, right? And the exam should become the error in the exam should come down, right? So it's the same thing that is happening. So we are training the model and then testing on the test book as well as on the exam, and we are observing the error in both, right? I hope this is clear so far, everyone. A question from Robert is training set size in percentage? Is basically a ratio, okay? And here, this one, train test split, okay? meaning if there are 100 records, 20% will become the test, and the values in the test will be the second ones. Okay, so this one train test split returns say 4 values. Okay, the the train and x validation, y train and y validation takes x and y from you, and also it takes argument like these argument test size and the random state. Random state is for predictable results, right? A question from Gonzalo is that okay, uh, how can you align train and validation is one is 80, okay, how can you align train and validation if one is 80 size and another? um, Good question. So basically the here we are basically computing the mean square error, right? We are basically computing the mean square error. So these are number of instances are different, right? The columns are same. All right. And since we are computing the mean square error, the vector is becoming the scalar. So if let's say here there are 10 records, correct? Let's say there are 10 records. It is going to have 10 records, while this one could have 200 records. This one is going to have 200 records, right? For each of the values of x, there will be a prediction on value here. So if this could be 10, this could be 200, while when we convert it into mean squared error, what we're going to do is we're going to subtract each value against the corresponding value. Like here, y predict, we are subtracting from y train m. You see this is the same number of records as there are, correct? And similarly here. So while we are doing the mean squared error, the two values that we are comparing have the same number of records. Okay, is it clear? No, it's a good question. So how can we, right? Is that your question, that this and this could have different dimensions? Yeah, so it doesn't, because see here, when we are predicting on M records, right? It's going to have M records, correct? And we are comparing with M records only, correct? We are saying colon M, meaning start this array from the beginning and go up to M records. All right. And similar thing here, Y prediction, Y validation is going to have 20% of the total records, right? And similarly, X validation is going to have 20% of the total records because our test size is 20, right? Therefore, this is going to have 20% record. Therefore, this is going to have 20% record. And so this is also having 20% record. So these two are equal. All right, good, great question. So moving ahead, so the learning curve basically demonstrate the idea that if you increase the training set, if you increase the training set, what will happen is the overfitting keeps on going down. Okay, but that's not always the case. If had it been algorithm like decision tree, probably the training set error would have been really low like this. Okay, really low like this, and the validation would be really high. Okay, so and so a straight line cannot do a good job modeling the data, so the error ends up at plateau. very close to the other curve. So if this error is really high and both are equal, that means your model is at least not overfitting, but your model is probably underfitting. Okay, and yeah, if the model is underfitting the training set, then okay, right? If the model is underfitting the training set, then add up more training data will not help. Okay, this is an important learning, that if your model is underfitting, no matter you gather more and more data, it's not going to bring down the error, right? We would need a more complex model or come up with better set of features. Okay, so if let's say this will not go down with the data, this is important. If we plot the learning curve of 10-degree polynomial model on the same data, this is how it is going to look like. You can see this, the difference. If we have 10-degree polynomial, this is how it is going to look. So what can you say about it? Yes? Anybody? Oh, looks like we missed the break. Extremely sorry about it. So I started talking. All right. And let's take a break and let's get started. All right. So great. All right. So if you take a look at the learning curve, you can see that there are two curves. One is for training, there is for validation, and on the x-axis, it is the training set size. On the y-axis, it's the root mean square error. All right. So here you can see that up to 10 records, it actually memorized everything, right? And up to 10 records, the the error on the validation set is really humongous, right? What else can you say? What else can you say about it? Which one is more overfitting, this one or this one? The previous learning curve or this one, which one is overfitting? This one or this one? That's right. Okay, what else can you say about it? That's right. Thank you, Sumit, Jay, Deepak, Al-Sayed. All right. So the error on the training set or the training data is much lower than with the linear regression model, the one which we saw earlier, right? Here you can see that the error is actually very low, right? As compared to the linear regression model. The gap between the two curves. So this means that the model performs significantly better on the training data rather than validation data, right? Which shows the model is overfitting. And the two curves continue to getting closer, right? So as the data is growing, these basically are coming closer together. And one way to improve the overfitting is to feed more training data. So to overcome the overfitting, right, until the validation reach the training error, right? Now, what was the error earlier? Error earlier in case of this, I'll just show you this one, right? The error was close to 1.9, probably, right? While here, the error on validation set is 1.4, correct? 1.4. So you can see that by increasing the degree to 10, the error has come down on the validation set, but at the same time, it is also overfitting. Therefore, there is a scope of uh, bringing down the overfitting by the various means, because you can bring down the overfitting, and you cannot bring down the underfitting. To bring down underfitting, you will have to um, move to a complex model, or move to a more I mean, basically move to a complex model. That's how you can overcome the underfitting. All right. Yes, the change the logic in the model. That's also right. Now, moving ahead, so you can see that there is a huge difference. There's a difference between the two, and therefore there's a scope of bringing down overfitting. This bringing down overfitting is called regularization. All right. So the model's generalization error can be expressed as a sum of the three different errors. One is the error that you're getting is maybe because of bias, maybe because of variance. Variance is in overfitting, bias means underfitting. So it may be because of underfitting, overfitting, or irreproducible error. So generally, when we talk about the model's generalization error, these are the three parts to it. These are basically three parts to it. One, maybe because of bias, maybe this model is because of it is not sophisticated enough. That is the one reason why we get there is an error. Second reason for the error is maybe it is memorizing too much, right? And therefore it's not generalizing well. And that's basically variance, or you can say the overfitting. Third part of the error is the irreproducible error. What is irreproducible error? The noise that we had, right? In our case, we created the noise by ourselves by adding some random values. That is the noise. This noise could be the error in taking readings, or sensor misfired, or I mean, or maybe there are some random factors in the environment. Okay. So question from Sumit is, could you please let us know what is the significance of this concept in real-time scenario? I mean, how can we distinguish with the given amount of data and requirement where to use these algorithms? Good question. So basically so this concept of learning curve applies to all algorithms, no matter what you use. And the whole struggle when it comes to the machine learning is about bringing down this error, right? So imagine that you are basically happily going through the end-to-end project, right? Let's say you want to predict certain thing for an industry. You're given the data, you have built the entire end-to-end project, and now you're observing that the error is not coming down, right? The error is not coming down, and there is a error, and the most of the machine learning projects revolve around bringing down the error, right? Bringing down the error, and so on. So when in those cases, when towards you have built the model and it's giving predictions, but you're not getting great error. So then you have to observe closely whether we need to make the model complex, or we need to force the model not to underfit, not to overfit. Okay. And at that point of time, you would need to plot these graphs and understand the behavior of your model. If you see this kind of one, you'll say that, hey, this model is definitely overfitting. Therefore, we can do something to make it better. All right. And this is true in all possible algorithms which we are going to use, whether decision tree, deep learning, the neural network, or any kind of anywhere. The entire machine learning, the core of machine learning is supervised learning. And when we talk about supervised learning, this concept remains there. And probably everything that we do as human is actually some form of supervised learning. Incrementally, we do the predictions, right? Similarly, if you think about reinforcement learning, that's also supervised learning. And uh, and in supervised learning, it's very core of the learning, understanding of learning, whether we are learning too much or learning less. Like, for example, in this class, I'm teaching you something. If you are really learning something, you will be able to solve the unseen problems, the problems that we have not learned in this class, right? And if you are able to learn only the things that we are teaching in the class, this essentially means that you are overfitting, right? So as the class is passing, right, the training set is increasing, we are learning more and more things. um, are we able to solve more unseen problems or more seen problems? Those are the two curves that we have here. All right. Most of the learning of the machine learning ideas is actually understanding of our learning as well. Okay. So a question from it is model testing in case to make it work efficiently. That's right. That's right. Okay. So when we are in the final stages and we want to see that, okay, now the model is ready, it's doing some predictions and it's doing some giving some kind of error. Now we need to figure out how to go about optimizing it. All right. So either we can go for making the model complex, coming up with better features, or force it not to memorize, right? Or let the error be, because if the error is because of random circumstances. All right. So this we have talked about these three things. So if right, so increasing a model's complexity increases the overfitting or variance. Variance and overfitting are interchangeably used, so get familiar with these keywords. And it reduces the bias in the sense that it basically is more in little bit more intelligent than the one that is having high bias. Conversely, reducing a model's complexity increases the bias and reduces the over its variance or overfitting. This is why it's called a trade-off. Okay, so this bias variance trade-off is going to be there in the entire process. Now, what to do when this is again a very important concept. Anywhere in every model, what we do is we beat down the model, we regularize the model so that it does not memorize, right? We force it, we put the constraint, we put the constraint on how much it can memorize. How we penalize it for memorization or overfitting, and we force the models to not memorize, to not have overfitting. All right, that's called regularization. And so what we do is, as we saw earlier, a good way to reduce overfitting is to regularize the model or constrain it. It's hard for a model to overfit the data if it has less degree of freedom, right? It is hard for a model to overfit the data if it has less degree of freedom. Now, this degree of freedom is an important part. Now, if we have, if we had lots of space to uh, memorize something, right? We have lots of huge memory, so the chances are that we'll end up memorizing everything. If we have the constraint saying that, hey, don't memorize too much, you can only keep this much of information, right? In that case, that we are constraining the model, right? So one of the ways one of the ways of forcing the model not to overfit is by reducing the amount of memory it can take, or reducing the degree of freedom. We constrain the model by we constrain the model by reducing its degree of freedom, right? For example, to regularize a polynomial model, reduce the number of polynomial degrees. When we have less number of polynomial degrees, what will happen is less number of thetas, and hence less freedom, and and therefore we are constraining the model, right? Because as we increase the degree, what happens is we got x square, x to the power 4, x to the power 5 in the same expression, and therefore those many coefficients, and hence there's a huge degree of freedom. So as we go for more polynomial degrees, we get so many thetas to train, and we get more freedom, and hence the chance that the model will overfit is very high, right? So for linear models, the regularization is achieved by constraining the weights of the model. So there are different ways to constraining the weights, like one is called ridge, other is called lasso, and third one is called elastic net. So uh, let's just understand L1 and L2 quickly. We have already learned it earlier. We talked about different performance measures. One was mean squared error. Other is called mean absolute error. Okay, mean absolute error is when in case of mean square error, what we did was we did square, right? We did a square on values. In case instead of doing a square, if we just take the absolute, in case it's negative, we take the positive. So so basically, so that errors don't cancel each other, therefore we basically change the sign of negatives to positive, so that all errors basically add on, and that becomes the overall um, the absolute value, right? So basically, that's called mean absolute error. Now here, do not get scared with this formula. It's actually a pretty simple thing, right? So what we are doing here is that, let's say we come up, what does it mean by mean absolute error? Let's say we come up with some hypothesis or model. This is our model. We feed it some value, it gives us the prediction. We subtract the prediction with that actual prediction. This is our actual value, and this is our prediction. So this is our y cap, the predicted value for each of the instances. Here we are going from first instance to mth instance, meaning we are computing, we are taking a row, and all the values of that row we are feeding to the model, all the columns of that row, the features, and then we are getting certain prediction from the model, and we are subtracting that from the label, right? And then whatever we get here, we are computing the absolute. Absolute means in case this value is negative, it'll become positive. In case this is positive, it will remain as such. And then we sum it up. We sum up this error across all the all the instances. So and then we divide it by total number of instances. That is our mean absolute error. Absolute means if we basically consider only the positive side. We basically convert negative into positive and sum it up. And error is delta between the predicted value and actual. Okay, so I hope this is clear to all. So both root mean square error or mean square errors are always to measure the distances between two vectors. Predictor values, vector and target. Okay, so predicted, actually not it's basically predicted values versus the target values. Is we basically do the delta between the two, and that's the purpose of it, right? Now, there are various distance measures or norm to calculate the distance between two vectors. One is called Euclidean and other is called Manhattan, right? I'll just describe these two. This is basically a very common term. So norm or distance basically is also called norm in terms of vector. So there are two kinds of distances. One is called Manhattan, other is called Euclidean, right? So let's say if we want to go from A to B point, if this was an empty ground, you can just start from A, go up to B, right? Like across the diagonal. That's that's basically the that's basically the Euclidean distance, right? This is Euclidean distance, right? And if let's say it was a city or a town and there are lots of lanes, you can't really walk straight from A to B. You'll have to go through the lanes or through these blocks, right? Then that is called the Manhattan distance. Manhattan distance is this one. You can see this is one Manhattan distance. This is another. This is another. You see this staircase. This is another Manhattan distance. Okay, the good part about Manhattan distance from A to B, that no matter which way you take, whether you go from here to here, whether you take this, the overall distance is going to be exactly same. Okay, this all of these will have the equal path. These all three lines that you see, except for this one. Okay, all of the Manhattan distances are equal, right? So when we talk about, let's say, A and B, if we subtract, how do we compute this distance? We basically do x1 minus x2 whole square plus y1 minus y2 whole square, and then do the square root, right? Remember the Pythagoras theorem, right? So that this this distance is essentially this distance that you see, the Euclidean one, is basically same as the mean squared error, while Manhattan distance is basically an mean absolute error. Okay, when we subtract A and B, and we basically, let's say here we are representing A and B by the way of two coordinates, x and y, because it's in two dimensions. If it has both A and B has, let's say, 1,000 columns, now then the distance, that way we can compute the distance, will be, we subtract each of their coordinates, right, with the corresponding coordinates, square it, and then do the square root and so on, right? That's how these two things are related. So while the Euclidean distance or is calculated using kind of Pythagoras way, and while Manhattan one is very straightforward, that we sum up the total distance from A point to B point, we can't really go diagonally, we have to go through this. So we just sum up. In this case, if you want to find out the distance between A and B, we basically find the distance between x, distance between y, right? Y1 minus y2, x1 minus x2. We sum up this plus this. Okay, that's Manhattan distance. While in case of the Euclidean distance, we say a square plus b square, and so and we do the. So in case of Euclidean distance, we square, and in case of Manhattan, we just sum up the absolute values, right? Is everybody clear? These terms are important because you will see lots of people talking that, hey, instead of using this performance measure, why don't you use Manhattan distance? Why don't you use why are you using Euclidean distance, or you are using this Euclidean one is called L2 because it has square, and Manhattan one is called L1. Okay, so Manhattan one is called L1, and it's also called absolute, and the Euclidean one is the one where we are doing mean squared and so on, right? So I hope, because these terms are become very confusing very quickly. So let's just keep that very, very simple. So L1 norm is computing the sum of absolutes, is called L1. Okay, it's denoted by two vertical lines, and it's called Manhattan norms. It's also called Manhattan norms, right? The L2 norm is computing the root of sum of squares, right? Root of sum of squares, root the mean square, the root mean square error, and it corresponds to the L2 norm. Okay, it corresponds to the L2 norm, or is denoted by, here it was one, two parallel line, two vertical lines and one, and here it's two vertical lines and two here, two suffix, or we can just use this. Okay, now as a generalization, there is something called LK norm. LK norm is when we are taking vectors, we are saying v naught to the power k plus v1 to the power k, and so on. And L naught just gives the cardinality of the vector, meaning 1, 1, 1, 1, 1. That's like total number of elements, right? And L infinity gives the maximum absolute value of the vector. Okay, so just as a generalization, you can keep this in mind. Okay, so LK norms, the higher the norm index, the more it focuses on large values, right? Because when the power of something increases, let's say square, one's square is 1, while 10's square is 100. Okay, similarly, if you think about cube, one's cube is 1 and two's cube is 8, right? While 10's cube is 1000. Right? So as the k keeps on going up, the degree keeps on going up, the higher values becomes far more higher, while the smaller ones do not play significant roles, right? 0.1's square is how much? 0.01, which is far more smaller. Therefore, higher values keep becoming higher when you have more bigger power introduced, right? That's why the root mean square error is more sensitive to outliers than mean absolute error. But when outliers are exponentially rare, like in a bell-shaped curve, the root mean square error performs very well and it's generally preferred. Okay, so L1 can lead to a sparse models while L2 does not. Sparse models help in feature selection, which features are important, which features are redundant. Okay, let me try to correlate this with a meaningful example. So a number of times sometimes we have to decide whether to go with L1 or L2, right? Whether to compute the mean square error or whether to compute the mean absolute error, right? Mean squared error is generally, as a thumb rule, everybody uses it. Okay, while the mean absolute error is rarely used. It can yield to more. It can give you more sparse models, meaning which can give you um, because it is more resilient to outliers, and therefore your model could fit the outliers also, and sometimes we want to basically figure out the features of which features are important, which features are redundant. In those cases, L1 is generally better, but as a thumb rule, we'll be mostly using the mean square error. Okay, a question from Bo is that what is the main reason to use GLM, and what regularization do? Okay, and okay, basically in very simple word, regularization, with regularization we try to bring down the overfitting of a model. Okay, and we're just learning L1 and 2 for it. I'm going to give it more context as we go ahead. Okay, so L1 is basically where we compute the absolute, L2 is where we are computing the square. Now let me just give you a proper meaning of regularization. All right, The first variation of regression, the GLM, the general linear model, right? That's what it means, right? GLM is a term from R. And the first variation is the ridge regression. What does regression? It's basically a little bit tiny variation of regression, whereby we regularize regression, right? Because you saw in case of degree of 10, it is started overfitting, and there is a chance that we can bring it down. We can force it to come down and improve the model. Okay, if the model is overfitting, there is a chance of improving the model. And how do we do that? By the way of regularization. And one such regularization is ridge regression. Now, in ridge regression, basically is a regularized version of linear regression, nothing much. A regression term is added to the cost function. Now, this is important. So what is done in this is that we had certain cost function. Remember, the cost function was predicted value minus predicted value minus the actual value, the square of it, and then we sum it, right? That was our the the cost function or loss function, or a target function, right? That we will come up with thetas which minimize this particular error or cost. Correct? So now into that, we do a crazy thing. We add this extra term. Okay, why are we adding this? We are penalizing. We are telling the model to minimize this also. We are telling the model that while you're minimizing the error, minimize this also, right? We are telling that, hey, the error minimization is good, but minimize the total thetas you have. Okay, while you are figuring out thetas, keep in mind that your error is, you're going to be penalized if you have thetas too big. Okay, now this is something very uh, different, or very uh, makes you feel uneasy, because we were doing cost function normally, like we were coming up with the thetas which were giving us a certain error. We were trying to minimize, we were trying to tweak thetas in order to minimize the error. Correct? That's what we were trying to do, coming up with the model which fits the outcome. But here, what we've done is we have added this regularization term, which is the cost function, to the cost function, meaning when we are telling our gradient descent that, hey, come up with the thetas which minimize the error, we are telling that the come up with the thetas, come up with those thetas whereby this term also is reduced. Okay, Bo, are we on the same page now? Everyone, are we on the same page? So what is this term? This term is nothing but sum of all the thetas that we will come up. Okay, and yeah, this will make more sense. I'll just go back. So this is the cost function. Earlier the cost function was only this, mean squared error. Now the cost function is this, meaning come up with those theta. We are telling the gradient descent that, hey, come up with that algorithm, that we're telling it that, hey, while coming up with the thetas, right, do not only minimize the MSE but also minimize this. Okay, come up with those thetas which have minimum squared sum. Okay, we are telling the model, we are telling the gradient descent that, hey, while you are computing the error, now your error also has one extra variable here. Okay, which means that you don't have too much of degree of freedom, because if you are increasing theta too much, this value is going to be higher, and therefore your error is going to be higher. Therefore, keep thetas, the overall squared sum of thetas, to be as small as possible. So we are asking we are forcing the model not to have too much of degree of freedom. Okay, by the way of curtailing its degree of freedom, we are curtailing or we are limiting its overfitting. Okay, the more degrees of freedom algorithm has, the more will be its so the more the freedom it has, more will be the overfitting, right? So we are telling the model that keep the thetas as close to zero as possible. Okay, we are telling the let's say when we are going to use gradient descent, what are we going to do? We are going to compute the rate of change of j with respect to theta, and and basically that'll be the value. Now since it's a squared one, so the outcome will have some positive value. Therefore we'll have to minimize thetas in order to minimize the error. Correct? So here essentially, in order for the model not to memorize too much, uh, not to have too much of freedom, we are penalizing it, right? So that's the idea. Let me just go over the theory quickly. So this is the regulation term. Adding a regulation term to the cost function forces the linear learning algorithm to not only fit the data but also keep the model weights as small as possible. Note that regularization term should only be added to the cost function. So while we are training, only at that point of time we penalize it so that thetas are kept smaller. Okay, and once the model is trained, we evaluate the model's performance using the unregularized performance measure and so on. Okay, so why did we add the regularization term during the training, not while evaluating? While predicting, we don't add this term. It's only used at the time of training. All right, keep this in mind. You will see this happening again in the deep learning, that we will be doing regularization only during training, not in testing. Okay, so the reason is cost function should have optimization. Basically, I think this is clear to everybody. No? Al Sayed, Arun, Bo, Deepak, Gonzalo, Jay, Nikita, Prashant, Robert, Robin, Satyajit, Sumit. So feel free to let me know if you're getting the regularization or not. I would like to explain it a bit more. Question is, we don't want to overfit the model using training set, but you want true RMSE for testing. Correct. That's right. All right. So is everybody on the same page? All right. So idea is very simple, that we want to force its degree of freedom. And one of the easiest way of forcing the degree of freedom to lower is by limiting thetas. Now, the second, this ridge regression term, this regression term could be smaller when either of the theta, some of the thetas are zero, or some of the thetas are decimal numbers, or let's say lesser than one, okay, or lesser than -1. Therefore, when we compute the gradient descent of this, this is always going to force us to keep on bringing down the thetas. All right. A question from Sumit is that, do we regularize models to make sure they respond to new set of data and solve other problems? Yes. Regularization of the models is such that they respond to the new set of data, new instances, that's right, and solve other problems. That's correct. That's correct. And question from Bo is, what is the theta here? 1 of x? No, the theta is basically the coefficients that we are trying to predict. Those are the weights. Okay. So we have to, I mean, this okay, let me just talk about like here, right? This one, right? So we were given some x1, x2, x3, right? And our y is some function of some some function of x, correct? x1, x2, x3, and so on. In case of linear regression, we say that, okay, it's going to be theta 0 plus theta 1 into x plus theta 2 into x2, this is x1, plus theta 3 into x3. So these are our thetas. Okay, basically the model is what the model parameters, the one that we are figuring out are the thetas. So we are basically adding weights to our coefficients. Yes, so we are saying that the error that we have, J, we are putting the, this was the usual one, this was our usual one, that whatever is the mean square error, right? Whatever is the mean square error, like y predicted minus y actual square and sum of it, that's the mean square. And to that, we are adding one more big term here. Okay. Now here there is an alpha that you see. Did you see alpha? Now this alpha is the one that controls how much regression do we want. It's one of the hyperparameters that will say that, okay, ridge regression alpha, the coefficient of ridge regression is going to be 1, right? In case it's like 10, it's good, this function is going to have huge impact. If it's 0, then it'll not have any regression, okay? Any ridge regression. So basically this alpha that we have multiplied here gives us the ability to turn off or on ridge regression or increase the amount of regularization that we want. All right. So ridge regression is just a linear regression, okay, with extra term. If you put alpha equals to 0, then this becomes like standard linear regression. Note that the bias term theta naught is not regularized as the sum starts at I equals 1, not 0. We are just constraining the weights of features. Hence, regularization of bias term is not required. Okay. So yes, we are adding the weight to our error function. Okay. We are adding the weights to our error function, and while minimizing the error, we are also keeping in mind that not to go too high on the thetas. All right. Okay, so it's a one part that note that the bias term theta naught is not regularized as the sum starts at I equals 1, not at 0. Okay, so theta naught is not regularized, not want to penalize it based on theta naught, and because we are just constraining the feature weights, uh, weights that multiply with each of the features. Hence, regularization term, bias term of regularization is not required because bias term is not being multiplied with any of the x1, x2, x3. It's not like here. Okay, this one, you see, this is not being multiplied with any. This is theta 1, not v. Handwriting is a little bad. Okay, and this theta naught is the bias term, and that's not regularized. All right, so moving ahead, that's correct, Deepak. All right, feel free to ask questions because that's the only way we can learn. If the if the W is the vector of feature weights W to theta 1 to theta n, then the regularization term is half of the W2, as in the L2 norm. Okay, then it's basically the L2 norm. Okay, so basically the same thing that you see here is essentially written as W or weights, and these two lines represent the L2 norm with the 2 here. Okay, and I'm just wondering why there are square. Ideally, there should not be any square here. All right. One important thing with respect to ridge regression, when you are applying any of these regression techniques, make sure you scale the data using the standard scalar, okay? And or using the even the min-max scaling is good enough, not only standard scalar, any of the scaling will do good. Before performing any kind of ridge regression, because ridge regression is sensitive to the scale of input features. Okay, so make sure that before doing the regression, or anyway, when you are doing the gradient descent, you will prefer to always have the scaled data. Scale could be using standard scalar or min-max. There's no constraint on that. Okay, so let's train the model using ridge regression on some linear data using different values of alpha. Okay, a question from Deepak is when to use min-max and when to use standard scalar. The value, when the values are going really high, like going crazy high, as in 0 to 10 and 100 and so on, then using standard scalar will make more sense, right? Using a standard scalar will make more sense. Otherwise, min-max scaling is also good. The other thing is then when it's a good question. So when to use min-max and when to use standard scalar. And other thing is that there are certain algorithms, specifically the things like neural networks, in which you would like to have strictly the values between 0 and 1, right? In those cases, we prefer the min-max. Otherwise, we prefer the standard scalar also. So standard scaling or min-max scaling, either of the two is good enough in most cases. Okay, but lots of people seem to use standard scalar more often than the min-max. So except for when you're using neural network, people use min-max, and otherwise people generally go for the standard scalar because if the values are too high or too big, you don't want to be going with the min-max. Okay, so yeah, either one is good enough. Okay, just that when your data, even you do not have any idea about your data could be varying too much, go for standard scalar. And that's one of the reasons why people prefer going with the the standard scalar. And only in case of neural network, you will use the min-max scaling. All right, perfect. Now moving ahead, let's train models using ridge regression on some of the this. Do we have this in our notebook? We should have. Okay, so now here, what we are doing is we are creating this method called plot model. Here we have created a pipeline. Remember the pipeline we talked about earlier, that we could have multiple things in a chain. First, this will be done. The output of this one will go to this, and then that to this. So here we are fitting it, meaning first of all, we are introducing the polynomial features, and then we are doing the scaling, and then we are regularizing the model. I mean, running the regularized model, right? And when we say fit, it's going to fit this, fit this, fit this, all the three things. And we will get this model, which is basically trained on this data. And once we are done with that, we can do the model.predict and we get the outcome here, right? So if LW is 2, LW, okay, so let me just take a look at it, what we are trying to do here, specifically this piece of code. But the core is that we are going to run the plot model with various arguments. So let's take a look. Here we are saying that plot model, we are saying ridge. Okay, we are passing the model class, correct? And then we are telling it that polynomial is false, meaning turn off on this particular one. Okay, so we are saying polynomial is false, the second argument, and then we are passing some alphas 0, 10, and 100. Those are the alphas we are passing, right? Remember the alpha value we just talked about. And then we are passing the remaining model arguments. See that? All right. So this is the list of alpha values, and this is the whether to turn on the polynomial or not. And this is the class, right? So here we are saying that for each of these alphas, we are going to iterate over the list. What is going on here? We are zipping this list. So if these alphas are going to have 3 values, so each of them we are going to combine with this as a tuple, and then we are iterating over those tuples. So first we are going to go with say here 0 with blue, 10 with green, and 100 with red. Okay, so we are saying that first do all of this for alpha equals 0, then do this all of this with alpha equals to 10, and then with 100. And what's going on here? We are first of all we are calling this model class. We are creating an instance of this class, right? We are creating the instance of this class by passing the alpha, right? Okay. These model arguments are extra in case you want to pass it forward. So whatever is being passed to us, we are further passing all of those to the actual model class. Like it could be linear regression. Right now it's ridge. So ridge, we are instantiating the ridge object model here. And then if the polynomial is on, then we create this model. Okay. Otherwise, the model is this one. Okay. And then we fit the model, and then we do the prediction. And once we are done with prediction, we basically plot it. And that's where we get this kind of model, right? So here, there are 2 plots, this and this. This one is non-polynomial, meaning linear. This one is the polynomial one. And what kind of polynomial is this? Okay, so the polynomial is with degree 10. So this is this is degree 10, and this is the non-polynomial one. Okay, and these are the various values of theta alphas: 0, 10, and 100. 0, 10 to the power minus 5, whatever we have passed here, and alpha. So now let's take a look and read the observations. Okay, so this is the plain ridge model leading to linear predictions. Okay, so you can see that here this is the without any ridge regression. And this one is with ridge regression little bit, and this one is a heavy ridge regression with alpha equals 100. Right? So what we see is that this is the polynomial regression. So polynomial regression with ridge regularization, you see that when we have alpha as 1, this is a heavy regularization, right? This is lower, this is even lower, right? So right, so data is first expanded using the polynomial degree, that we have added more and more columns, and then we did scaling, and finally the ridge models are applied in this. So what is your observation? What is your observation, anybody? A question from Deepak is, we are selecting higher alpha values for linear regression. Good question. There is no reason to it. It's just empirical that we figured out that with the significance of alpha, significance of alpha is more in case of the ridge regression here, in case of the polynomial, right? Therefore, we are keeping the alpha a little lower here. That's basically totally empirical. After trying to plot it, to have trying to show a meaningful difference, we have done that. All right. Now moving ahead. So this is the ridge regression essentially. In this ridge regression, we basically, what we are trying to do is we are trying to see here there is no regularization because alpha is 0, right? So the line is happily going like usual way, right? As the alpha is growing a bit, what's happening is the line is being pushed down because it doesn't want too much freedom for that. So these lines are being kind of flattened. Now you see alpha has 1, it has become kind of a straight line. See that? It has kind of become the straight line. So you can see that as we are forcing it to regularize, it is it is basically being constrained and is becoming like a straight line, right? Remember the straight line, it has only 2 degrees of freedom. One is the slope and other is intercept, the two variable, two thetas. But in case of polynomial degree 10, they're going to be 10 thetas, correct? They're going to be 10 thetas and they're going to be 10 degree, huge degree of freedom. But the moment we put the constraint like regularization term, we are saying that don't increase thetas too much. And that's what is constraining the degree of freedom. All right, Sumit. So degree of freedom means it's a conceptual, it's just a concept or a general idea whereby we say that more number of variables to train in a model or more amount of memory that a model holds is the degree of freedom of a model. More things to train in a model is basically more degree of freedom. All right. Yeah, you can think of it that way, that degree of freedom is like that, right? The more bigger area you have, the volume, the bigger area you have, the more is the degree of freedom and so on. Similarly, here we are saying that thetas cannot go beyond a certain value and therefore thetas don't have a huge degree of freedom and therefore we are not letting it just memorize the noise. A number of times model basically thinks the get fooled by the random values, get fooled by the I mean that noise, and it memorizes that, and we keep thinking that. So we were talking about ridge regression. So essentially we want to constrain it. Now what we did here is that we did a square of it, L2 1, and yes, this part we have discussed. So like linear regression, we can perform ridge regression either by computing a closed form equation or by performing gradient descent. Either one, like either we could say the normal equation or using the gradient descent. Either of the two we could do. All right. And if we are doing the ridge regression, basically there's an extra term. Extra term in case of closed formed solution, we get an extra term here. Okay, and essentially this is a kind of identity matrix whereby we have an alpha because there will be thetas here. All right, so this is essentially how we calculate this. All right, it's not mandatory to memorize this, just to know that yes, there is a normal equation way of solving it. In the normal equation, we basically introduce one more term, alpha a, to in order to get the normalization or get the regularization done for the ridge regression. The important part is to understand one thing, that so common question or common question of people in the interview or any discussion is around regularization, right? The question will be that you'll be shown a graph, specifically the learning rates graph, the one that I showed you, the learning curve. whereby there is a the error on validation data or error on the testing data, and you'll be asked like, hey, given this kind of data, what do you think is the problem? And once you notice that, okay, it looks like this is overfitting, right? Looks like this is overfitting. Why don't we uh, do something about overfitting? Then the next question from the interviewer will be that, what would you do in case of overfitting? We'll say that we will regularize. So then the next question will be that, what do you mean by regularization? Then you say that you curtail or you limit the freedom of the model. And how do you limit the freedom? By decreasing the degrees of freedom, such as by reducing the number of thetas or constraining how much value can go with, can change for thetas. And how do you do that? One of those is, in case of regression, in case of regression, we have things like ridge regression and others. And in case of decision trees, we have other mechanism. In case of deep neural network, we have things like dropout, which we will study further, and so on. All right. So that's the common way of why the regression is, why the ridge regression is important. So I'll just walk you through a similar one. So you can actually implement this. It's not mandatory to know this. And basically here, when we derive this equation, it is definitely possible to derive it, but it's not really required to know that part. All right. And the identity matrix is basically like this, the one that has all the diagonals as one, rest of the things as zero. And this A is essentially the the identity matrix, except for zero here, and that's all. All right. So the way this is important to know is that we could simply say ridge and alpha a equals 0 as argument. And this solver is Cholesky. There are multiple solvers. Historically, if you are using the normal equation, which is not good if you have too many features. And in that case, in that case, the normal equation may not make sense. But if you are looking for normal equation, use solver as Cholesky. I'm not sure if that's the right pronunciation. And then random state is also optional. So here, this is how you specify that you are looking for. Uh, you're looking for ridge regression. So you say ridge, and then first argument is alpha. If you provide alpha is 0, then it'll behave like normal regression. All right. And once you're done with that, it'll give you the results. Now, if you want to do instead of going with the normal form, if you want to use the stochastic gradient descent, the stochastic gradient descent regressor, you could use SGD regressor. And here, notice this: penalty L2 means ridge regression. Okay, penalty L2 means ridge regression, and we can pass the random state as argument. That's optional. Now that's pretty much. And so here penalty means L2, L2 means ridge regression. And also here also you could specify alphas. You could also pass an argument saying alpha is this. Okay, now that's how you could do ridge regression. And now on the same lines is lasso. In lasso, instead of square, it's modulus, or you can say norm. And here also there's an alpha coefficient, and the combination of the two is called the elastic net. Elastic net is a combination of both of them. Okay, this is ridge regression as not this is the, what was the name? Lasso. Okay, this is lasso. This term belongs to lasso part, and this is the elastic net. And you say that, okay, if some part of this, you put a fraction term that if this fraction is 0.5, this will be considered. If both will be considered 50-50, and so on. So combination of the two is elastic net. All right, so that's what is the regression. And after regression, we're going to talk about logistic regression that's used for classification, converting any regression model into the classification. We use a technique called logistic regression. All right, we will talk about from here tomorrow from lasso regression. A question from Sumit is within all right, so that's pretty much for today. I'm going to answer your questions. Those who have questions can stay back, or those who want to listen to each other's questions, please stay back. And in case you have a hard stop, just let me know so that I can also do a hard stop right away. All right. So a question from Sumit is with an example, can you please let us know post uses of regularization, how the model predicts the new data set, predicts the new, if the degree of freedom is less and we're putting constraint on polynomial higher degree. So we will explain this. It's a good question. And we will explain this by the way of these graphs. So you'll be able to see the values, the error, how it's going. You can see that by comparing this is the polynomial regression with lasso regularization. You can see that. Okay. So if the degree of freedom increases, this is what happens. And in case of this, if the degree of freedom increases, what's happening is it has become kind of horizontal. The impact of other x is no longer there on the y value. We are left with only probably what do you say, a theta, not the bias term. We kind of, it kind of ignored the impact of axis. Okay. So question from Sumit is, so we first deploy on some data set, right? So the way we do is that we go with Elastic Net, we consider whether to use lasso regression or not, or whether to use Elastic Net, how much, so whether to use rich or lasso, we basically tune it using the hyperparameters to Elastic Net. Okay, the next one basically has the option to turn on or off the regression and so on. So we consider basically, we start with our model, we do the end-to-end project, we start predicting, then we realize that, okay, there is a regularization need in our problem. So what we do is we use instead of normal regression, we just use the Elastic Net class. It's as simple as that. And then we basically do a grid search to find those hyperparameters for which we are getting the best results. All right. All right. Bye-bye. Have a good day.